Welcome. So this lecture we're going to look at incompressible flow. This is assumed in many different areas, not just because it's convenient, but because it's a good approximation in some cases, in particular at low speeds, compared to characteristic speeds like the sound speed. So this is cases where the fluid as it moves around is not being squashed, it's not being compressed or expanded. It's just moving smoothly through past any objects we've put in there. And so we're going to look at several different concepts to explain this. The convective derivative we come across before. This is the change in a quantity as it moves with the fluid. The Mach number, which is the ratio of the flow speed to the sound speed. We're going to look at more, or start to look at more rigorous ways of understanding this. And for example, the characteristic scales are what are the typical length scales, the typical time scales, and typical velocities. And we can use this to normalize our equations and understand which terms are large and which terms are small. And then this is used in a more rigorous approach called singular limits, which we'll only be able to cover in a very superficial way here, but hopefully be an introduction. And the main question we want to answer is, when is flow incompressible? When is this a good approximation? And we can try and understand this by looking at cases where we have a flow past an object. So we have an object which is in a stream. So we have flow past this object. Now if you have a flow onto an object like this, there's going to be an increase in pressure at the front because the fluid is pushing on the fluid. And that pressure perturbation will travel through the fluid at the speed of sound. So if you have a kind of a change in pressure at one location, it will propagate through the fluid and move outwards through the fluid at the speed of sound. And so if the flow is very slow compared to the speed of sound, then that pressure perturbation will propagate a long way upstream. Now if the flow becomes comparable to the speed of sound, then this pressure wave no longer travels very far upstream. And in particular, once you go supersonic, so once the flow is faster than the speed of sound, then the pressure waves cannot travel upstream from the object. And so in that case, you end up with a very large compression of the fluid as the fluid essentially comes into here and then hits the front of the object here. Whereas in the slow speed case, the pressure wave starts to deflect the flow over here before it reaches the object, and the flow just smoothly moves around the object. So you start to understand this by looking at some of the equations involved. So you start by looking at the pressure equation. So how does the pressure evolve in the fluid? And here we'll just use the Euler equations. So if you haven't seen these before, just go back and have a look at the earlier lectures. So I'll look at the pressure equation. And so we have dP by dt. So the change in pressure with time as the fluid moves through the past the object. Plus you drop grad P. So that's the change in pressure. This whole thing is the convective derivative, which is the change in pressure as you move along the fluid. And that is, I'll put gamma here. So there's 5/3 typically for an ideal gas. So gamma is the ratio of specific heats. I have gamma P and divergence of U. So if it's incompressible, that implies that this is 0. So divergence of U just means that the shape, the size of a particular box of fluid is not changing as it moves. The box is deforming and changing shape, but the volume inside is not changing. And so this is 0 for incompressible. And so that means that this whole right hand side is 0, and so this says that the pressure in a parcel of fluid, so I have a little bit of fluid here, has a particular pressure P. As it follows this line here, then the derivative along that line is given by this quantity here. So the derivative along this line, and so as the fluid moves along here, the pressure is constant. So pressure constant is constant along the flow lines. So as you follow any particular flow line, the pressure will be constant. And the same for the density. So the density equation looks very similar. You have a divergence of U on this side, and so the density is also constant. So here I'll just put rho is also constant along the flow. So both pressure and density are constant. Okay, so we can try and understand this more mathematically by looking at the momentum equation. And so for a fluid we have so du. So this is the momentum equation, so du by dt plus u dot grad u. I'll make it a bit clearer here. So du by dt plus u dot grad u is 1 over mass density equating to pressure. Okay, so we can try and understand this in essentially what's going on along the fluid. So we can look at this in one dimension and start with a steady state. So for steady state flow, so steady state flow, that means that this time derivative goes to 0. We can look at one-dimensional flow, which simplifies this. So if you have just flow, say along a streamline, or flow in any direction really, so this just becomes a single derivative. This becomes a derivative along the flow lines. This becomes the gradient along the flow lines. So we have basically u. You might just call it the x direction, for example. So now d ux by dx. So this is this. So if you have u in the x direction, then take the derivative of u in the x direction, you get this. Well, ux means the flow in the x direction. It's minus 1 over rho dp by dx. Okay, now we can make some fairly simple adjustments to this equation, and we can essentially use this to work out how does the velocity change and how does the pressure changes. How are the velocity changes related to the pressure changes? Now I'm going to miss out the dx's and just consider just write it as du and dp's, just for notation makes it easier. But what we can do is we can essentially write this left hand side as so we can write it as ux squared, and then we need to divide by ux. So I'm going to take the dux and divide by u. So this is the ratio of the change in the velocity to the velocity. Okay, so I haven't done anything, I just put in a ux and take it out again. And the same here, I can put in a pressure and take it out again. So you have a minus p over gamma, p over rho bodies. P over rho. And then here we need to take out the p again, so we have a dp and a p. So this is the ratio of the pressure changes to the pressure. And this is starting to look a bit like the sound speed. So this p over gamma, so p over gamma is just the sound speed squared divided by gamma. So p over rho. So because the sound speed squared is just gamma p divided by rho. And so this is the sound speed squared divided by gamma, where gamma is the ratio of specific heats. And this now, we can just pull this over to the left hand side, and so we have that ux squared from here divided by cs squared, and we get a gamma is coming over here. Then we have a dux by ux. Ux coming here, and that is just equal to minus dp by p. And this says that the ratio of the velocity changes is related to the ratio of the pressure changes, so the relative changes in the pressure, by this factor here. Now this factor is is the square of the ratio of the velocity to the sound speed, and this is the Mach number squared. That's where m is the Mach number. Which is equal to u as the speed divided by the sound speed. And so you can see that as Mach number, if Mach number is small, effectively then the pressure changes are very small. And so you can have large changes in velocity, so from the typical velocity down to 0, for example, sort of stopping velocity. And if this Mach number is very small, then the changes in pressure will be very small. And this is related to the internal and the kinetic energy. So U squared is essentially related to the kinetic energy of the fluid, and then here the pressures are related to the internal energy. So the kinetic energy and the internal energy. And so if there's a large amount of kinetic energy in the fluid, the motion of the fluid, then we have a very high Mach number. And if we have a very high internal energy, then the pressure is very large, and they have a small Mach number. So the Mach number is related to the ratio of the kinetic energy and the so the Mach number squared here is essentially the ratio of the kinetic energy to the internal energy. Okay, so this means that if Mach number is small, so i.e. much less than 1, then dP by P, so is the relative pressure changes. This is the pressure changes are small. Okay. And hence, if you go back to this equation up here, where we had this here. So here we said that if we have incompressible flow, then the changes in pressure are small along the flow lines. Here we're saying that this happens when Mach number is small. So if Mach number is small, the pressure doesn't change much as the fluid moves, and hence the compression term in the on this equation is small.